One. Okay, now, welcome everyone to Zoom for Thought. Thank you, Itai, for coming to speak to us this week. We're now going to hear about some topological quantum computing and the Toric code. Take it away, Itai.
Okay. Before we start, we should just clear up all the words that I'm gonna misuse and how like this is going to be both kind of physicky but not really physics and mathy, but like it's gonna be pretty mathy actually. But it's the lies are mostly in the physics parts. So we start with what is a qubit, just to kind of start things off. And in quantum mechanics, you have Hilbert spaces and things and that. But let's restrict ourselves a little bit to just starting with the basic unit of quantum computing, which is a qubit. A qubit in the physics world can be thought of as like an actual particle with spins and things, but for us, it's going to be a copy of C2 with a choice of a favored basis we're going to call 0 and 1. And we're going to refer to this as the first one, and this is the second one for like any matrix notation. So like, for instance, this matrix takes zeros to ones and ones to zeros. This is our choice of basis. What do we deal with in quantum mechanics in general? What happens is we kind of always projectivize Hilbert spaces. We at the end of everything we always take like the Hilbert space that we deal with, and we just mod it out by like the kind of projective action. You know, the action of C on C2 in the standard way, so that this actually corresponds in the real world to CP1. So that's what a qubit is. That's all we're going to think of it. You can think of it as an electron and these as the up and down spins or whatever, but we're not. We're just going to think of it as a copy of C2. What is a quantum computer then? What do we think of when we think of a quantum computer? We think of a bunch of tensor qubits. Tensors of C2. Again, each one with their choice of basis. That's their canonical basis. That's what they got for them. And so we tensor all these, and in this case we do the projection at the end. And so that this is basically the identification of this with C2 to the n, or I guess that's not really well defined. C to the power 2 to the n. And then the projectivization gets us to CP 2 to the n minus 1. And that's more or less where we start with, right? This is a quantum computer in the most mathy terminology has a Hilbert space, or this has some kind of Hilbert space associated to it, and what we care about is unitary actions on this guy so that we can use those to compute in some nice way. That's the basic bare bones definition. The first problem you get with this thing, so the first problem you get is errors. Basically, the idea is if this is an actual quantum system that's real and exists, and you can make it out of like actual like electrons and stuff, well, everything is going to interact with it. If you're interacting with, if you're talking about an actual Hilbert space for an actual quantum system, and you have, you know, a slight amount of heat, well, that already makes some operator on this tensor space, right? This tensors of copies of C2. And if you have an operator on this, if you have just a random operator on this, it can literally do whatever. You lose almost all of the information with the smallest error, right? Because let's say you just have some unitary operator. Well, there's literally a continuum of unitary operators. But let's say you can even restrict it so that it only messes with, you know, somehow like similar to how normal error works in real life, it only messes with the last little bits, you know. So we have, like, let's say that we have a single copy of C2, which we were just going to call, let's say the first number is 1 plus I, or I don't know, 1 plus I pi, comma 3 over 2 e plus 45i, and then we projectivize at the end, whatever. Let's say we have some kind of operator on this that kind of kills all of the end terms out. We see we lose almost all of the information. Might as well just be a normal computer once we have this, because once these things are finite, we've lost all the real gains you make by looking at quantum things as opposed to finite things. And so the question is, how do we deal with errors? And the answer is, of course, we cheat. You can't actually deal with errors, right? Because there's going to be any amount of them of any kind, right? And so instead of just dealing with a specific error, a specific kind of, instead of just dealing with like any kind of error over all of the unitary matrices on C2 to the n, we deal with specific ones. We start with the Pauli matrices. If you've seen them before, I'll just write them down. Sigma x equals 0, 1, 1, 0. Sigma z equals 1, 0, 0, minus 1. And sigma y we don't care about, because there's gonna be some multiplication with i's and things, but even that we don't really care too much about. Is right? Yes, I think this is right. Okay. The idea here is that if we think of every error as being composed of some amounts of sigma x's and sigma z's on certain qubits, and some adding of those, some subtracting of those, like, every error can be composed as sigma x times sigma z, like some kind of like what is the best way of saying this? The best way of saying this is really saying that if we look at a single qubit, a single copy of C2, we look at the operators on this, so SU2. The SU2 has a basis, the identity matrix, sigma x, sigma z, and I believe it's sigma z, sigma x. This basis, I believe, over the complex numbers, which this is basically sigma z, sigma y. The end result is, if we can, the big assumption, really, the big cheat, the big lie that we deal with here, is that if we can fix if we can fix sigma x and sigma z errors over over a certain number of qubits, that means we're doing a good job. And the best case scenario is if we can fix an arbitrary number of sigma x and sigma z errors. That's kind of what is considered to be winning in this case. How we're going to limit the problem so that it's actually solvable in real time by real people.
Hey, Itai.
Because otherwise, it's an impossible problem.
Can you reiterate what a sigma x error is?
Oh, sure. Let's say your Hilbert space is just tensors of C2, right? Some kind of. So let's even make it simple. Let's just say it's C2 tensor C2. And let's say we just consider sigma x, tensor the identity, applied to this matrix, applied to the space, right? Now, if we have this applied to this space and we have certain information in there, right? If we have certain information in C2 connected to C2, and this is applied to it without our knowledge, this corrupts the information. With information that was once here, we don't know what it is anymore, right? If there was, for instance, if the numbers we had before, 1 plus I pi, 3 over 2 e plus 45i, was the information in one of these qubits, and this happened to it, afterwards we can't be sure about our information, and any chance of doing actual computations with this immediately doesn't work, because you don't even know what you're supposed to have.
Okay, so like you have this 2-particle state or n-particle state, and the error associated with some number of sigma x's and z's is just an application of the appropriately tensored sigma x, sigma z onto that state.
Yeah.
Okay, cool. I got
exactly.
It. Thank you.
That's what an error is. It's the application of a function that you're just saying is the functions that you care about applying.
Gotcha.
The idea, of course, being that there is some good reason to think that these are all reasonable functions that will act on this space, or that all of them are at least generated by the applications of enough of these. Okay, so this explains to us how we're going to limit our problem. Now let's go through an actual way to solve such a problem. And this is where we get into the actual Toric code. So I guess donuts are relevant now. Okay, so the way we actually solve this problem is we consider a torus. We consider the flat torus in this case. And we consider a lattice on the torus. A lattice in this case not being anything particularly math, like subgroup of something, just kind of a square lattice from the normal, how do we call it? The normal kind of physics world. Anyways, we consider a lattice on such a torus, where again this edge is identified with this edge, and this edge with that edge. We then associate to every one cell of this thing. Let me change my color back to blue. We associate to every one cell here. For instance, this we can call a one cell. We associate to every one cell a qubit. So for every one cell, we associate a qubit. For every two cell, we associate an operator, and same thing for 0 cells. I'll explain the operators in a bit, but let me get to the main idea first before I actually get to what these operators are. The idea is that if we look at these operators for every 2 cell, which my thing needs to connect. So if we look at the operator for every 2 cell, let's call these operators B2s and these A0s. If we look at these B2s and A0s operators, what we're going to want at the end is we're going to want the homology of the space, H1 of the torus, to in some way be associated to the one eigenspace, the common one eigenspace of all B2s and A0s. So this is for every single 2 cell, there's a different copy of B2, and for every single 0 cell, there's a different copy of A0. And the common one eigenspace of all of those choices, we're going to somehow associate to H1 of the torus. And in fact, we're going to try to associate in such a way that we don't really even use the fact of the torus, so that this can actually be generalized to really any chain complex. And in fact, this can be entirely done by looking at a generalized algebraic chain complex over Z2. This is all going to be over Z2, and the Z2-ness is going to be important. But let's just start.
Just to clarify, the B2s and the A0s, they're just something in your construction, and everybody commutes with everybody, which is why there's a common one eigenspace.
We're going to have to show that, but
yes.
Okay. Yeah. Yes, that's not necessarily true, but we're going to see that it comes right out of the fact that this is going to be a chain complex. But let's just look at the torus first before we do anything fancier, because why not start where it's all easy and nice?
One question, sorry.
Of course.
So the choice of B2s and A0s, do we pick them arbitrarily, or
no? I'm about to say exactly what they are.
Okay, I see.
Yes, and yeah, okay. So B2, and we'll even call it B2I for some 2 cell I, is going to equal. It's going to be a bunch of tensors of the identity in a bunch of places, and we're going to tensor wherever we don't tensor the identity. It's just going to be let's call it J in the boundary of I, and there it's just going to be sigma x. Now this, if you've seen this before, you'll notice that this is not actually the one that people choose. Normally they choose sigma z for this one. Let me just rewrite sigma x and sigma z for you guys over here. Sigma x is going to be this one, and sigma z is going to be this one. In a lot of things, they actually use sigma z here. The result is exactly dual. It doesn't actually fully matter for the error correcting code case, which is what we're doing. We're doing this is called an error correcting code. It's a construction on a certain set of qubits that is made to correct errors. So this is for everything in the boundary of the ith 2 cell. We're just going to apply sigma x's, and everywhere else it's going to be the identity. Correspondingly, a0 of I for some 0 cell I is going to be the tensor of the identity everywhere that we don't really care about, tensored to sigma z's, and the sigma z's are just going to be on J in the co-boundary of I, co-boundary being the 1 cells on touching the 0 cell I. Okay. So for instance, for this 2 cell, right, if we associate B2 to this 2 cell, we will do sigma z here, sigma z here, sigma x. See, I got it confused in my switching things up. Sigma x here, and sigma x here. And if we look at this 1 cell, we'll just do sigma z here, sigma z here, sigma z here, and sigma z here.
Question?
Okay. Yeah, go for it.
What is the big tensor over?
What do you mean this tensor? This is over the rest of the qubits in the lattice. For every other qubit in the lattice, we just do the identity as the map. So this is just over the qubits that are in the boundary of I, we do sigma x.
Cool. So you're picking a discretization and considering the homology with respect to that discretization.
Well, I mean, the homology is going to always be that of the torus regardless.
Right.
This is more of a way to actually get those things to add up in terms of the Hilbert space of like some kind of qubits and the actual homology of this thing.
So actually, Itai, you say for every 1 cell I. So the number of C2s in the underlying C2 tensor power to the n, that number n is the number of 1 cells in your lattice. Is that right?
Exactly.
Okay, sweet.
Thank you.
Yeah. For every 1 cell, we associate a qubit. Every 2 cell, an operator, and every 0 cell, another operator. And the qubits are again this. The operators are this and this respectively. Okay. Now, how do we actually show that this works? Well, let's just start with looking at some some basis vectors for this space. So let's do this on the next page. Basis vectors for tensors of C2 to the n, I equals 1 to the n, these can just be given in our canonical basis vector form as some kind of zeros, tensors, ones, and so on. You know, things with zeros and ones tensor together in such a way, every such choice is another basis vector of this space. It's quickly obvious to see that this works. This is what tensor products are. And it's all fine and dandy. Again, it should be noted that each one of these C2 comes with a canonical basis. Then we can see that these the B2s, when acting on some kind of basis vector, what they do is they switch the zeros and the ones. And so if we have a copy of the torus, and we look at just a single 2 cell, and we look at this, maybe this is a 0, and a 1, and a 1, this will take the zeros to ones and the ones to zeros. Okay, so at this point, it should be mentioned what the homology, how we're looking at this in terms of homology, right? In terms of homology, what we're doing is basically the same thing. We're associating, we have the following chain complex, Z2 let's call these two cells faces, Z2 edges, and Z2 vertices, right? And here there are certain boundary maps. Let's do some better notation. This should, at the very least, add up with all the other notation that I've seen. And we have some kind of boundary maps. And here, what do we see? Well, we see when we apply B2 to some basis vector. No, let me go back a bit. Let's associate to each state zeta, which is some eigenstate of C2n, or some basis vector in this. For zeta, basis vector in tensor C2 I equals 1 to n, we associate, we look at all the ones, and we associate to zeta the element in Z2e, which is just the sum of those one cells. So zeta goes to all the, so let's just so zeta goes to the sum of EI, and this is the I guess the ith part of zeta is 1, or the ith qubit in zeta is a 1. All I such that the ith qubit in zeta is 1. And that's kind of a ugly way of seeing this, but I don't really know of a better way to state this kind of association. Maybe a quick example is pretty easy to see. If we have just some kind of C2 cross tensor C2, and we have a state, let's say 0 tensor 1, it will just go to the edge associated to this guy. So it would go to, in this case, E2, the second edge, if that makes sense. And so I guess the better way of seeing this is that maybe I'd even, oh no, I don't want to erase. Maybe the better way of seeing this is something like 0 tensor 1. 0 is, let's say, let's just assign labels to the edges that are associated to it. Tensor 1 dot 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 will go to E1 plus E4 plus dot 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 in terms of the homology, or in terms of the chain complex. The idea being that this is a 0, so it doesn't go to anything, but the 1 goes to E1, the 0 goes to nothing, but the fourth one goes to E4, if that makes sense. Now what this means is that if we look, yeah.
So these are E1, E4. These are formal sums. Yeah. This is
yeah. These are formal 1 cells.
Okay. Cool. All
these
good.
are formal 1 cells of this space, or if not the space, but this I guess this vector space. Now the idea here is, well, what does B2 do on some state, some basis vector? Well, what it does is it just adds, or it switches these, but that amounts to adding a copy of everything on the co-boundary, or everything on the boundary. And so what we see is, if we have some state like this and we apply B2 to it, B2 on some zeta, the image of what happens on this kind of association is we get E1, or we get let's call this map F for, let's call this map F. F of B2 of zeta is just going to be F of zeta plus the boundary on, and this is for the ith 2 cell, the boundary of the ith 2 cell. And so what this means is that when you apply this boundary map to this, you can see how if we want the space for the one eigenspace here, it's going to have to be an equivalent. It's going to have some kind of relationship with the equivalence class of all of the things of all of the images of the boundaries of faces. Because for each such face, if we take the boundary map of said face, it's going to be and add it to this association, we get they should kind of mean the same thing, because we want this to act as the identity. And what that's going to mean is that if we just look at if we look at the torus and we look at just the ones, right? Let's make a picture of just it's the same picture corresponding to before, but now we just look at the ones for some basis vector. Let's say these are where the ones are as opposed to the zeros. If we just look at the ones, we see immediately that this association means that if we want B2 I of psi to equal psi for a general element in the protected space in this one eigenspace, we're going to need to take the sum over of this space of this choice of ones plus the choice of ones for every closed one cell and every choice of closed one cell. So we're going to need the space corresponding to this as well as the space corresponding to this. And we can see we can do this continuously, or not, we can do this like this many number of times and get every such state. And doing B2 twice will get you back to where you started. And so the first thing we notice is that the state we need, I guess, all the way back here to associate to the state that we need to be in the one eigenspace of B2A0 is going to be the specific state that is going to be the sum over all of these co-boundaries, over all of the B2s applied to a certain basis state. So let me just write this down. The one eigenstate of all B2i's is I guess really a one eigenstate is generated from a set basis state. In this case, a bunch of zeros tensor to ones, ... and let's call this state psi, and the sum of and the sum, let's just write the sum phi equals sum of B2I psi. I is in the two cells. What are the set of two cells? The faces.
So is this some sort of, are you doing some sort of, this is like just taking some sort of averaging thing over all of the...
Yeah, it does. It is effectively taking the averaging over all such things, but you can see that each one of these things are going to be, if we look at the association in the homology, each one of these things are going to be different elements here, which are in the same equivalence class. If you look at the modding out by the image of this map. That's kind of the big point. It's that we're averaging these things, but each one of those elements in the average are the same under this equivalence, under this under the modding out by the image of this map. And so that's how we're going to get the first half of the homology going on. Does that make sense? The second part, this part is going to be kind of the easier part, and it's going to be how we're going to see that we're going to get loops. That part just says that for any zero cell, we can look at the co-boundary of the zero cell, so the edges adjacent to the zero cell, and we can see that since we're doing sigma z's to those, which is of this form, we can see that we have to have an even number around any zero cell. And what that means is if we look at just the ones from before, these ones will have to become loops, right? We can't have something like this, because then this zero cell won't work, and this zero cell won't work, because at those zero cells, this sigma x applied to all the ones around it will change the whole change the state to that state times -1, and same with that one. And so what we see here is that any possible choice of basis state that we choose must have the fact that must have all the ones in some kind of loop. They must form a cycle in graph theory words. And so what we get is we get that all of the all of the one cells, when we look at just the ones of the one cells, they must form loops of some kind. And so together these two things say that what we actually have here is that every state that's going to be in this one eigenstate has the ones, if we just look at the ones, as loops of some kind. And if we apply B2i's to these things, we can see we can make new loops. We can make new loops, but they're still going to be contractible. And the B2i's will kind of give us this kind of idea of homotopies, right? If we apply like a B2i to this, we can see we can kind of change this loop and extend it. Oh, sorry about that. So like, let's say we have some kind of loop like here, and we have like some kind of 2-cell here. If we apply B2 to this 2-cell, we kind of take this last bit out and extend it a little bit. And we can see that if all of them end up being loops of some kind, contractible or not, this is going to be able to allow us to make homotopies between said loops. And so what this leaves us is that, well, it leaves us a couple of things. First, it leaves us that we're only going to look at things that are in the kernel of this map, because this is going to be the boundary map of an edge, and we need 2 edges, or an even number of edges, along any zero cell. And so every single and so I guess the main point in the end, the very last bit that like is needed to actually construct this thing, is the idea that the protected space, this one eigenstate, the one eigenstate of A0i's and B2i's, let's call this L, has a basis of the form psi equals sum over, these are going to be all states, all homologically equivalent states for, let's call this psi I, all, and we can even make this a bit more particular, all states homologically equivalent to psi I, or homologically equivalent to some element of the homology of the mesh, all states equivalent to some homology of the mesh, and for every non-trivial how do I want to say this, non-trivial element in H1 of the chain complex we made before. And the way to see this is that the sum we take over here is literally the sum over all of these b's applied to any the sum that we take, or sorry, let me actually go to this page. The sum that we take is the sum of any b's applied to the to some basis state of which is made of loops, and so we get all such. We get all the homologically equivalent ones because the b's kind of act as this as the image of the map, and they add in contractible loops, and so they do nothing to the homology, and the a's kind of mean that that you're looking at things in the kernel of the next map, that you're dealing with actual loops. And so I guess that's kind of this is kind of the big point where L has a basis of this form, and so L is actually equal to, as a tensor product, tensor of C2, where I equals 1 to H1 of the underlying space. And I guess in this case it's T2.
Question?
Yeah.
So each basis state is a basis vector for that huge tensor product where you tensor C2 for every edge inside the simplicial complex you choose.
Yeah.
So when you apply B2 to it, do you flip the 0 qubits? Do you flip the sign of the zeros or the ones?
You flip the zeros to ones and the ones to zeros.
You flip the zeros to ones and ones to zeros.
Yeah. So the explicit thing that happens is if you just look at the ones, right? We're just going to outline the ones here, and let's say we apply B2 to like this 2 cell. Let me erase that and replace it in red.
And so each basis vector inside this huge tensor product corresponds to coloring each edge with a 0 or 1 in your simplicial complex.
Yeah, and that's exactly the point. And the big thing that happens is that if you color them this way, the fact that the A's, these are the one eigenspace of the A's, means that all the ones have to form loops. And the fact that you do the B's means that there's the things over the sum will have to be, each one has to be homologically equivalent. Yeah, they have to be homologically equivalent elements over the sum. Does that make sense?
I was wondering, how can anything be an eigenvector if you have to flip the zeros and ones?
Oh, I mean, the eigenvector is literally, I mean, the simplest case is this. 0 plus 1 is an eigenvector if you flip the zeros.
Oh, right. Cool.
Right, and that's kind of what happens when you apply these B2s.
Right. So when you write that phi with the angle bracket, it's not necessarily a pure tensor.
So this psi, or
yeah, the psi, yeah.
So the psi, in this case, it is we start with a pure tensor and we apply these B2s, and this is what happens. And I guess I have been mixing from pure tensors and not pure tensors this whole time, which isn't great. But this phi here is not the pure tensor. This phi is like the actual element. But the psi, we start with some pure tensor of this form, and then this phi is going to be not a pure tensor.
Right.
Yeah. So yeah, this is the main crux of the thing, where you actually get the homology corresponding explicitly to the subspace. I kind of want to keep going a little bit further if this is not too confusing for people. I feel like I've made it more confusing than it has to be.
Yeah, like in Twin Peaks, I'll give you the Cooper's thumbs up. Thank you.
I guess the next thing to really talk about here is why does this actually work? What does this actually do for us, right? Why did I make this whole construction? Who cares at all? And the answer is actually pretty simple. If we look at this thing, if we look at these this torus with these identifications, now how many errors can I detect now? Well, let's say we have some kind of sigma x error on this qubit right here. If I check this 2 cell and this 2 cell, I'll see an error. And if I check this 0 cell and this 0 cell, now I see another error. And so that means I can start to find errors by looking at checking these set operators that I started with, and even more so, if I that's only with one error, but now I can actually detect up to k errors I can find by if they're by I can both find and fix up to k over 2 errors, where k is the size of the lattice, by just looking at them, and if they're in a row, then I just squeeze them together with the shortest path between them. And that means that now this state, this system, is protected from the lattice size, let's call it k, over 2 errors. So if this number of errors happen, you can always just take the errors and put them together the closest way you can, and it'll if there are sigma x or sigma z errors, they will just kind of collapse in on themselves, and you'll get back to the state that you started with, because the result will just be equivalent to some BPs or ASs being applied to the system as a whole. And so you can fix errors now.
Wait, so I guess I thought I was following, but maybe now I'm confused. So you start from your initial quantum state, and then you build the lattice from that?
So we start with a lattice where we have placed qubits on each edge.
Mm-hmm.
Okay. And on this lattice, we have defined a certain operators that we want to be one eigenstates of this lattice, such that the only things that are protected, the actual information is hidden in explicitly. It's hidden in the sum mod 2 of the number of ones along any non-contractible loop.
So
that's where the information is now
kind
hidden.
of the quote unquote message space that you're allowed to use is only this one eigenspace. Like, I'm just thinking in terms of, if you just go back to classical error correcting codes, right? You have a bunch of messages and you encode them into some higher dimensional thing that you can correct errors from.
Yes.
So in this case, what you're encoding is the one eigenspace into this larger torus, and that's giving you error correction?
Yeah, it's giving us error correction because at this point, if there's any error on any one cell, right? Let's say there's this one cell that there's an error on. The fact that we have these operators, we can see from those operators that if this one doesn't actually act as identity anymore, because a sigma x was happening here or a sigma z was happening there, we can now see that there must be an error in this specific one, and if there's an error, we could just apply that same operator again. And so now we can fix that error that way. This is actually called syndrome measurement in the field. But yeah, that's the main idea. And the issue is, the only time where this doesn't work is if you have a bunch of errors going along a non-contractible loop. If you have a sigma x's errors along a non-contractible loop like this, what you have is that there's no errors in any of these 2 cells or any of these zero cells, because along such a loop, everything still has an even number of things in the co-boundary and the boundary respectively. If it depending on how you do it, it's in this case these would have to be sigma z errors along this kind of loop, and sigma x errors along this kind of loop in the dual lattice. But that's not actually super important right now. But that's the main idea. If we look at a loop like this, if we look at a ribbon, so to speak, a string of z errors, let's call that sz of t, for t being some kind of path along this thing, and just sigma z's along all of these. Well, this obviously commutes with any sigma z operator, and so we can kind of ignore the what was it? The A's, the A zeros. But for the sigma x's, it does not commute, it anti-commutes, so it has to go along 2 of them. Anti-commutes the sigma x's. And what that means is that if you look at some BP, or B2, sorry, if you look at some B2I that intersects this path, it must intersect it at 2 places for this not to commute, for this to commute, and therefore not be detectable. And so if it has to intersect at two places of some kind of thing, like of some kind of any two cell, if we look at this two cell specifically, right, the loop will have to be something like this for us to look at this two cell and have it so that so that the B2I for that two cell and SZT equals SZT of B2I, right? And then if these commute, we can see that we can't really detect it in any real method, because any of these operators that we have to actually like use to apply to this thing don't work. And in more physics notation, what we kind of really do here is we're really thinking of the Hamiltonian of the system as kind of 1 minus the Hamiltonian of the system we're going to set as equal to the sum for any two cell in, let's call them faces, of 1 minus the A's was the ones for the B's were for the faces, and for any zero cell J in edge or vertices, we're going to do 1 minus A. And so here we have made an explicit Hamiltonian where the ground state is this protected state. And so now we've more or less made a physical system here where the ground state of this physical system has like four kind of different bases, which each correspond to the homology of the underlying like manifold. And I think I'm out of time, so if we have any questions.
All right, let's first thank the speaker. All right, any questions?
I have some questions. So the first one is that this solves the following problem, if I understand correctly, that previously, if you did a measurement, you lose information about sort of all the other states that are present. But after doing this construction, you still do measurements and you can retain something?
So no, actually, this does not solve any problems with really measurements. It solves problems with accidental operators happening from outside. Measurements are a more complicated and different problem, and the way you kind of deal with them here is you will have to do like a measurement at the very end of the operation. So you can do operators by doing these Pauli matrices around non-contractible loops to actually operate on these things. And there's another more interesting way to actually operate using like knot theory and things, which I was thinking of getting into. But in this case, that's how you're going to do operations. And then at the end, you can make an actual measurement by seeing what the values are on two non-contractible loops to see what happens to actually the logical qubits themselves. But this doesn't solve any kind of problem that you might have with trying to. There's kind of a paradox here where you can't really when you lose information because of measurement, you actually like lose information because of measurement. There's nothing to like fix it, and that's kind of a thing that just kind of happens.
Okay, I see. The other question I had is that you said that this can generalize to any sort of CW complex as long as
not even any CW complex.
Like any chain complex.
Any chain complex, as long as, and this was a thing that Vaki asked a question about earlier to show that these things actually commute. If you have any such chain complex like these, just of these, and you do these same operations, you associate qubits to these, you associate boundaries to these, by the way we did before, and co-boundaries to this, the fact that these two boundaries commute, the fact that these two boundaries are zero means every face has to touch the boundary of a face has to intersect an even number of the co-boundary of a vertex. And what this means is that if you associate operators in exactly this way, and that's kind of why I did this a bit more confusing construction, is because really what we've done here is created every they're called CSS code. Once you have that the boundary of the face and the co-boundary of a vertex intersected at least at an even number of places, an even number of edges, that means that these operators will always commute. And that means that everything else that we've done, that we've talked about all works in this entirely generalized thing where these edges can be gross and ugly, and there are very many cases. Recently there's been a lot of work in this field that like opened up a whole bunch of things and was based off the idea of making these edges be these kinds of generalized edges where you have a single edge with 3 like vertices coming out of it, where this is like one edge somehow, you know. And edges can be gross, faces can be gross. As long as these double boundary maps are 0, this construction will still work by just following everything I just said, a bit more slowly probably, but yeah.
Okay, I see. Okay. So in that case, you'll be able to show that such a choice of operators exists for that particular chain complex.
Using the exact same choice of operators,
Okay.
and you'll get
Okay,
exactly
okay,
the same
I see.
kind of homology coming out of it directly.
What is the dimension of the protected state compared to the whole state?
So in this case, it's 4. The dimension of the protected space is exactly equal to C2 to the power of h1 of t, and really, when I say h1 of t, I really mean like the first Betti number to be specific. So beta 1. However, it can quickly be seen by just taking connected sums of these guys that you can do a pretty good job at getting this to be substantially larger. By just taking direct connected sums of toruses, that everything else still works perfectly well, but now for that homology, which is going to be C2 to the number of connected sums times.
Are there
2.
any kind of bounds, like in the classical case, where like you can only do so well if you want to correct one error?
So there are set bounds similar to this. I don't know them exactly. I do know that people have been doing substantially worse than the set bounds for quite a while, and the amount that we can do right now, the best case for right now, is so we're able to do it in the previous case. We can solve k errors with k squared qubits. In the current best case, and this was just done like a month or 2 ago, is if we have O of n, or sorry, if we have n qubits, we can solve n divided by log n, O of n divided by log n errors, and have O of log n. This is big O, I'm just drawing it small. O of log n logical qubits, so to speak, or protected space things. And they even did a little bit better where they did an alpha here for some alpha less than 1, and 1 minus alpha here. So this is the current best case for if you start with n qubits, you can actually mess up the system enough so that the size of the minimum number of errors you need to actually destroy the code is this much, and that this is the actual amount of logical qubits you're using. The issue with this is, while the previous case is very easy to decode, you can quickly just notice that there's an error here and an error here and just take the shortest path between them. And even if you go around an error, the big thing is if you go around an error, you might have a problem. Even if you go around an error in this case, you're fine. You just add a phase to the thing, which doesn't do anything to the actual things that you measure at the end. So in that case, it's just the decoding is just connect errors together, and as long as there aren't k of them, or k over 2 of them, you're good. In this case, the decoding, I believe, is still an open problem, because they've fully messed it up a whole hell of a bunch.
Sweet. Any other questions? All right. Let us thank the speaker once more. All right. I'm going to stop the recording now.